All right, let's jump straight into this explainer. If you've ever stood next to a massive industrial motor, or, even just felt that tiny vibration engine buzz inside your smartphone, and thought, how in the world do invisible electrical currents create such a massive amount of physical force? Well, you are definitely in the right place. Today, we're unpacking the core principles of electromechanical energy conversion, really digging into those foundational concepts of electrical engineering. We're going to make the invisible visible, literally tracking the entire journey of magnetic fields.
So we're going to start with a pretty massive question, one that really sits at the heart of all electromechanical energy conversion. How exactly does an electrical wire move a heavy physical machine? I mean, it's not magic, right? And it certainly doesn't happen directly. There's this absolutely essential invisible middleman involved. Energy literally has to be translated from the electrical domain into a magnetic field, and then from that magnetic field into actual physical motion. Here's a quick look at our roadmap for today. We're covering 1. Translating energy into motion. 2. Mapping the magnetic circuit. 3. Navigating the air gap. 4. Inductance and stored energy. And finally, number 5, mastering magnetic materials.
Okay, Section 1, Translating Energy into Motion, and the 4 device types.
The big takeaway here is that whether it's a super delicate microphone transducer or a giant continuous generator, that magnetic field is your essential middleman. Engineers generally group these into 4 main types. Type 1 devices are transducers. Think microphones or sensors. These need high linearity because they're dealing with really tiny, delicate signals. Then you have Type 2, which are force-producing devices like solenoids and relays. These are built for intermittent bursts, like a switch violently snapping shut. Type 3 is all about continuous conversion, your classic motors and generators giving you a steady, reliable output. And finally, Type 4. These are transformers. They don't actually create motion at all, but they use the exact same magnetic principles to step voltages and currents up or down. But here's the thing. To make any of these work, engineers can't just let magnetic fields wander aimlessly around the room.
Moving right along to Section 2, Mapping the Magnetic Circuit and Guiding the Invisible Medium.
I absolutely love this parallel because it's a total game changer for design. Just as Ohm's law tells us that voltage pushes current through electrical resistance, well, magnetomotive force, or MMF, pushes magnetic flux through something we call magnetic reluctance. It's exactly the same logic. Instead of ripping our hair out of our crazy complex 3D vector fields in free space, we can just model the machine as a simple circuit. The electrical current in our wire creates the push. That's the MMF. The resulting magnetic field is the flux, acting just like our current. And the material that field travels through creates the reluctance, which is the perfect equivalent of electrical resistance.
Now, imagine a perfect continuous setup. The flux is completely trapped inside a high permeability core, making a perfectly closed loop. This is your ideal magnetic circuit, exactly the kind of thing you'd find in a Type 4 transformer. The core is made of a metal that has a permeability literally thousands of times higher than the surrounding air. And because magnetic flux is, incredibly lazy, it always takes the path of least reluctance. So nearly 100% of that field stays safely trapped right inside the core, flowing smoothly and linking perfectly with our windings. It is highly, highly efficient.
Which brings us to Section 3, Navigating the air gap, or the leap across space.
But let's be real. To make things actually move, we have to break that perfect solid loop. You obviously can't have a rotating motor if the spinning part is solidly welded to the base, right? We have to introduce an air gap. And adding that air gap introduces a massive amount of reluctance. It's so high that the gap basically dominates the entire system. To put some numbers on it from the source data, the permeability of a typical metal core is around 10 to the negative 2 henries per meter. The air gap, 10 to the negative 6. That means the air is thousands of times more resistant to the magnetic field than the metal. When engineers calculate the total reluctance, the metal core becomes almost a rounding error. That tiny gap of empty air dictates exactly how hard we have to push to get our flux across.
And because of that intense reluctance, the flux doesn't just jump perfectly straight across the gap, it bulges out. We call this fringing. Think of it like water blasting out of a hose. It doesn't just stay in a perfect cylinder, it flares out. Magnetic fields do the exact same thing when they hit the resistance of an air gap. Interestingly, this fringing effect actually widens the effective area of the gap, which slightly lowers the overall reluctance. It's just one of those messy realities of physics. Design engineers actually have to use practical, empirical formulas, like literally just adding the gap length to the cross-section dimensions, just to accurately model it.
Okay, on to Section 4, Inductance and Stored Energy. Let's look at the dynamic consequence of all this.
Up until now, we've just been looking at static snapshots. But energy conversion means motion, and motion means things are changing over time. This step-by-step breakdown of Faraday's law beautifully illustrates how a changing magnetic field essentially forces an opposing voltage into existence. When the flux inside our core is fluctuating, say it's alternating at 60 Hz, it links up with the turns of our wire. This flux linkage induces a voltage across the terminals. But here's the crazy part. That induced voltage is actively trying to create a current that will oppose whatever change is happening to the magnetic field. It's a constant push and pull, and that right there is the fundamental mechanism of electromechanical energy transfer.
So that brings us to inductance, our L. You can think of inductance as the perfect metric for our circuit's efficiency. Measured in henries, it basically bridges the gap between the electrical current we pump in and the magnetic flux linkage we actually get out of it. If we have a circuit with a huge air gap, that high reluctance means a much lower inductance. It's a direct, measurable value of how well your specific physical geometry, the core, the wires, the gap, creates a usable magnetic field.
And here is the real payoff. The formula for stored magnetic energy. W equals 1/2 Li squared. This shows us exactly how a magnetic circuit acts like a temporary, measurable battery. When we push current into the coils, we are doing physical work to establish that magnetic field, and that energy is stored in the magnetic circuit. And get this, it's largely stored in the air gap itself. Then, when the field collapses, all that energy is handed right back to the electrical circuit. This exact transient storage mechanism is what makes AC motors and transformers even possible.
Finally, Section 5, Mastering Magnetic Materials and the Microscopic Reality. Let's zoom all the way down to the atomic level, because ultimately, all these big macro-level formulas rely on the bizarre quantum behavior of metals. Inside ferromagnetic alloys, like M5 steel for example, you have these microscopic atomic regions called domains. They act like millions of tiny little compass needles just waiting to be aligned. In an unmagnetized piece of steel, they're pointing randomly, totally canceling each other out. But the second we apply our magnetomotive force, we force those domains to line up, and as they snap into alignment, they add their own intrinsic magnetic field to ours, amplifying the total flux density incredibly fast. That's exactly why a steel core has a permeability thousands of times greater than empty space.
But there's a catch. We eventually hit a hard physical limit. If you trace the curve for M5 steel, you'll see that as we increase the applied field, the flux density shoots straight up. But eventually, right around 1.7 Tesla, the curve just flattens out. We have literally run out of magnetic domains to align. The material is completely saturated. You can push as hard as you want electrically, and you'll get almost zero additional magnetic flux. And it gets weirder. When we turn the electrical current off, the flux doesn't just drop back down to zero. The material remembers. Some of those domains stay stuck in alignment, leaving a residual field. To get it back to zero, we actually have to apply a negative current. This lag, this sort of atomic memory, is called magnetic hysteresis, and it is a massive factor when you're dealing with heat loss and efficiency in real-world machines.
And that leaves us with a pretty provocative question to end on. As we start really hitting these absolute physical limits of saturation and hysteresis, how will the microscopic realities of our materials shape the macro machines of tomorrow? I mean, we've seen how electricity becomes motion, how empty air gaps act like brick walls of reluctance, and how the actual atoms in our steel set the ultimate speed limit for performance. As we push for vastly more powerful electric vehicles and renewable energy grids, the next big breakthroughs probably won't just be clever wire arrangements. They're going to happen in metallurgical labs where we literally design new alloys to shatter the current boundaries of magnetic saturation. Thank you so much for joining me on this explainer. Keep questioning the invisible forces around you.